While the FOA primarily focuses on the cabling infrastructure used by networks, we often get questions on how networks work. Trying to read most online tutorials on networks is very difficult because of the technical level of the material and the incomprehensible jargon, especially the TLAs. That's an acronym we use facetiously for three-letter acronyms. So in this lecture, let's look at the networks, mostly LANs and the internet, and try to make it understandable. What is a network? Okay, so this mess of symbols and lines is a schematic of a network. Let's try to explain what we have here. On the right side, we have the users, the U symbol. Users can be many types of devices: laptops, tablets, smartphones, IP cameras, building security or management systems, and the like. On the left, we have the rest of the world connected on the internet. Let's look at how they connect. Today, many users use Wi-Fi to connect their devices. So those users connect through a wireless access point, the W on the diagram, with the connections shown as dashed green lines because they're radio connections, not cables. Users also connect with wired connections, the green lines, which are generally unshielded twisted pair copper cables or fiber optics. The wired users and the wireless access points are connected into switches, S on the diagram. Switches do what their name says, switch connections between devices. There are many types of switches depending on their complexity and how they operate in a network. Switches are generally cascaded, so there may be several levels of switching in a network. In the heart of the network, there'll be a switch or switches that connect all the users and all the access points, but also provides connections for servers and sometimes other high-powered computers shared in the network. And every network needs lots of storage, which may be directly connected to servers through the switches or connected into a storage area network, or SAN, optimized for handling storage. The LAN switches can also be connected to routers, the blue R's on the left side of the diagram, which are the smart switches of the internet, and that connects us to the rest of the world. Now let's look at how a network shares bandwidth. The essence of any network is that the network shares the connection and thereby shares the available bandwidth. For example, the mobile devices connected to a Wi-Fi access point share the bandwidth capacity of the access point. There are a number of different types of Wi-Fi developed by the IEEE 802.11 committee to allow higher and higher bandwidth. Wireless access points use multiple radio frequencies, just like any radio or TV broadcast, to connect more devices, and they use special techniques to allow higher speed transmission over the available radio frequencies. But wireless users don't want to just connect to each other, they want to connect to everybody. So the Wi-Fi access points are connected into the wired network by cables, the red line shown in the diagram, which would be UTP cable, copper, or fiber, just like other wired users. The wireless access point will be connected into a switch with other users, and they will all share the bandwidth available in the switch. All of the users in the wireless access points also want to be connected into the rest of the LAN. So every switch is connected into other switches closer to the heart of the LAN, again by cables, the red line shown, UTP or fiber, and all of the connected devices share that connection's bandwidth. Now we add another layer of switching, connecting other switches all connected into the backbone of the LAN. All of the connected devices share the bandwidth of the backbone cabling. The central switch has to manage numerous sets of users like this, sometimes thousands of them, so it will have many ports to provide backbone connections. Eventually, we get to the center of the LAN, where switching allows all users on the network to communicate with each other and with devices like servers and storage, and connect out to the internet. So now we have lots of connections, mostly wired, but some wireless, connecting everybody in the LAN. This is probably a good place to point out that wireless isn't wireless. It depends on wired connections beyond the Wi-Fi access point, and wireless is just replacing the user patch cord. Now, this type of network is generally called a star network, since connections go out of a switch in a star pattern. But when you have cascaded switches, a better description is a tree and branch network, which is the same description given to cable TV networks. And as you get into the tree trunk, connecting all the branches, you are sharing the backbone bandwidth with all of the devices it connects. Here we have shown the aggregated network traffic schematically by the size of the red lines. Since you are sharing the backbone bandwidth with all the devices it connects, the backbone is usually a higher speed connection than the branches it connects to. Here's an example using the currently available Ethernet versions. Not many LANs today use 100 gig Ethernet yet, but many are thinking about it. Most backbones are 10 gig, dropping to 1 gig for user and Wi-Fi access port connections. Wi-Fi access ports today need a solid 1 gig connection to support multiple users at the highest possible speeds, which are about 100 megabits per second on the regularly available devices. The internet is quite another thing. Billions of connected devices, unimaginable amounts of data being transferred all the time. The internet uses smart switches and multiple connection paths. The switches are called routers, and the connection is called a mesh network. This ensures you get the most efficient data transfers and the greatest reliability, because if one router goes out, the others can bypass it. Now many users are being urged to replace their servers and storage with cloud computing, where you move these services to data centers around the internet. Besides cost and security issues, there is another issue that few people are discussing. That's the connection of the LAN to the internet. While many LAN backbones run at 10 gigabits per second, most connections from the LAN to the internet are slow. Some users still have ancient T1 phone lines, 1.5 megabits per second, while most connections are in the 10 to 100 megabits per second range. A few lucky users are in areas where gigabit connections are available, but that's actually very unusual. It seems that the cloud depends on getting faster internet connections in order to handle all the traffic normally carried by the servers and the storage in the LAN. One variety of LAN is getting a lot of publicity right now. They're called passive optical LANs. A passive optical LAN is not a cabling system. It's cabling plus the electronics to provide network connections. Generally, those network connections are Ethernet, although triple play service, internet, telephone, and TV are used in consumer systems and some commercial applications like hotels or college dorms. A passive optical LAN uses fiber-to-the-home technology to emulate a switched star LAN. One way to look at it is that the passive splitter can replace a switch, allowing a single fiber to carry bidirectional signals to typically as many as 32 ONTs. These ONTs are basically small switches at the user work area, typically a 4-port Ethernet switch. The 32 split to 32 ONTs and 4 users each means that a single optical fiber can serve up to 128 users per port on the optical line terminal, OLT, which is the center of the network. Alternately, the number of users can be reduced to as few as needed to provide greater bandwidth per ONT. For example, connecting busy servers or storage. The OLT is a massive switch itself. Some are designed to handle 7,000 to 8,000 users or more, with the internal switching done on a high-speed backbone instead of cabling. Most passive optical LANs use the GPON technology, with 2.5 gigabits per second going downstream and 1.25 gigabits per second going upstream. Options already exist for GPON at 10 gig. EPON networks are symmetrical at 1.25 gigabits per second or 10 gigabits per second. Bandwidth allocation is different from Ethernet, which uses a collision detection scheme. Instead, it dynamically allocates bandwidth based on the polling of the ONTs. Optical LANs are becoming more popular, and FOA has a video already on YouTube about them that you should watch. This is just the first in a series of YouTube videos the FOA plans on networks, because we want to talk more about how networks allocate bandwidth and how they are actually implemented. So watch for these on YouTube, or go to the FOA website or the FOA online guide for more information. We're the FOA, the Fiber Optic Association, the International Professional Society of Fiber Optics.